Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Last time we went through special relativity and learned how space-time is changed by relative motion of two inertial frames. So an inertial frame, again, is a place where all clocks and all measuring sticks are all in a line and all lined up with respect to each other, and they're moving uniformly through space. And so they can either be still or moving uniformly. They're not accelerating or decelerating. Well, that's special relativity. But let's actually take another step, because we've actually talked extensively in the past about gravity. So gravity then is a different thing, because, well, when you drop something, it accelerates. It doesn't stay the same speed. You should try this at home. You should actually check it this way. When you drop something, how fast does it hit the ground? Does it hit it faster when it gets to the ground, or does it hit it slower? A way to do it is to drop something from a very short height. See how long it takes. You can then drop something from a larger height. Maybe it's something that's easy to drop, like a very small, like a lead ball or something that doesn't get much wind resistance. You'll find that as it gets to the bottom, it is accelerated and is actually going faster. And that is a result of the acceleration due to gravity. So gravity accelerates you downward. And the rate of acceleration at the Earth's surface is 9.8 meters per second squared. So for every second it falls, it goes 9.8 meters per second faster. So call it 10. The first second it drops 10 meters per second. The second it's 20. The third second it's 30, and so on and so on. So when you fall in a gravitational field, you accelerate. Well, what else did we find a long time ago that causes acceleration? We can go back to Newton's laws, Newton's three laws, and his definition of the force, not like force like Star Wars, but force. A force is something that accelerates a mass. And we also learned about from Newton that the force due to gravity is proportional to the two masses that are gravitating with respect to each other, divided by their distance apart between them squared. So here's the interesting thing, is that Newtonian physics says that for any force, it doesn't matter what it is, if you apply a force to a mass, it accelerates. And the resistance to that acceleration is what we call its inertial mass. So we can think of inertia as the quality of a thing not to change its direction or its speed, or how fast it's going, what its location, or how fast it's rotating, or or what direction it's going. So mass then is a measure of how resistant something is to accelerating. So if you know the force you're pushing with something, and you see what the acceleration is due to that on that mass, then you can determine the mass by seeing how fast it accelerates. Less massive things accelerate more quickly than more massive things, etc. But here's the funny thing, is that Newton also described the force due to gravity. And that's a very strange thing, because the force due to gravity also has the mass, and it has two masses, one versus the other. But let's look at them carefully for a bit. The first mass is what we call the inertial mass, and so you can take a mass, you can put it on a table and push it, maybe with like a rocket or something, or maybe a string pulling it or something like that. And if you have a string pulling it at a constant force, you have to keep accelerating as you move, but you can actually pull on something with a string. And that string will then, or however you pull it, that force will then accelerate the mass. Now that's across a table, so it doesn't rise or lower. The mass is simply the resistance to motion. Now wait a second, we take that same mass and we hold it above our head and drop it, it will accelerate also. And if we measure the force due to gravity on this thing, we would measure that it's the same mass. Now this is a strange thing, because they seem to be coincidentally the same mass. There are two different ways of measuring mass. One, resistance to motion across a gravitational field, meaning gravity has nothing to do with if it doesn't go up or down. Or gravity is always up and down. It's not side to side. You never hear of a gravitational force to the right-hand side of the room. You never hear about that. You only hear about falling due to gravity. You fall down. You go up against gravity. So gravity is not side to side. So how is it that the mass due to an inertial mass can be the same as a gravitational mass? All right, so Einstein came along in 1907 after accomplishing special relativity, and he said he had a couple of problems with Newtonian mechanics. And the first one is that if you look at, specifically the gravitational the force equation, he said, how does time figure into this? He already knows that from special relativity that nothing goes faster than the speed of light. It takes an infinite amount of energy in order to go faster than the speed of light, to accelerate something faster than the speed of light, or even up to the speed of light. So how is it possible that the gravitational force is communicated instantaneously? It doesn't matter how it's done instantly. So Einstein said, wait a second, you change the Earth's mass and it affects something on Pluto immediately. Well, he didn't know about Pluto at that. Well, he would have been about 20 years later. So he knew about Neptune. Neptune's very far away, and it's far enough away that it would take light hours to get to Neptune. But according to Newton, you shift something in Earth, maybe move Earth up or down fast, then Neptune, 40 astronomical units away, would feel that change instantaneously. That's faster than the speed of light, and so how can gravity's influence go faster than the speed of light? That was Einstein's first one, and the second one is that he said, as I described before, how can the inertial mass be the same as the gravitational mass? He said, well, the inertial mass is kind of like a resistance to acceleration, but the gravitational mass acts like a charge. Think of a charge as like the charge that you put on an electric charge. And so if you have an electric charge, this electric charge will determine the electric force between them. So you could say that gravity can be looked at as the charge of mass of two objects. How much force they pull is dependent upon the mass charge. Now, if we'd never had a concept of Newtonian inertial mass, or maybe we developed gravitational mass first, we might have thought of terms of mass as a charge, as opposed to anything else. We said, oh, mass is just the charge of an object that resists acceleration. So it's kind of an odd way of talking about it. But the important thing is that we cannot actually, it's a starting point where the inertial mass is not necessarily the same thing as the gravitational mass. There's no instantaneous reason to say they are the same. But Newton didn't posited that they were. He just said, well, Newton didn't know why gravity worked. He said, I have no idea why it worked. I don't frame any hypothesis about how gravity worked. I just know that these equations do work. And so they were extremely successful. Newton's theory of gravity was an extremely successful way of discussing things. And nobody really saw a problem because the gravitational worked just fine. Let's see what some of the successes. It explained Kepler's laws. It explained the motions of the planets. It explained the Earth's precession as it rotates on its axis, how the Earth precesses. It explained the tides on the surface of the Earth due to differential gravitational pull by the moon and the sun. It predicted the orbit of Neptune, the existence of Neptune, which was then later found. It also, even most dramatically, predicted the return of Halley's Comet to the day. So Newton's laws of gravity and motion are extremely successful, and they do seem to describe our world as we know it. But there's a couple of odd problems with Newton's laws, and they were waiting on the horizon for things to occur. One of them is this action at a distance idea that needs to be answered in some way. And then the strangeness of the equation of inertial mass versus gravitational charge mass. But there was another observational issue. Mercury, in its orbit around the sun, has its orbit doesn't quite close. It's got an elliptical orbit, but when it gets back to the perihelion, it actually is farther along. So the orbit itself precesses. It makes like a flower shape as it goes around and around, rather than an even ellipse. So Newtonian gravitational theory, as well as Newtonian mechanics, says, oh yes, if we add up all the effects of all the other planets and the distance from the sun and the effect of the distance of the gravity from the sun as it goes and check all the possible influences, yes, we can account for the 531 arc seconds per century of precession of Mercury's orbit around the sun. So the position of the near point to the sun changes by 531 arc seconds which is an angular measurement, per century. Now, here's the problem. This Newtonian mechanics doesn't predict the actual value. The actual value is 574 arc seconds. So there's 43 arc seconds, almost an arc minute, almost a portion of it, a significant portion of a degree that is lost. It's like almost 1/60th of a degree, maybe almost like 1% of a degree that is lost, that Newtonian mechanics cannot predict. And so people were thinking, wow, we need to modify Newtonian mechanics in order to fix Mercury's orbit. And so there were some people going off and thinking in those terms. But Einstein came along and said, wait, it's an acceleration. Mass gets accelerated. So if mass is accelerating, we're starting to think about it, because when you drop something in a gravitational field, it accelerates. So there is something about dropping things in gravitational fields that gets them accelerating that might be linked. So Einstein then said, now wait a second. I see that Newton says that the inertial mass and the gravitational mass are different things, but he says that they could be the same, or they're coincidentally the same. They don't have to be the same, but by sheer coincidence, and these were Newton's own thinking, is that by sheer coincidence they seem to be the same. That was the consensus. So Einstein, in 1907, to start down the road of general relativity, said the following. He said it as a postulate. He said they are the same. The inertial mass is the same thing as the gravitational mass. Now that might not sound like a big deal, but just think about how you can accelerate things. You can accelerate things not using gravity. And sometimes when you have and you can balance a force due to gravity by something that is not due to gravity. And so however you measure their forces, they're the same. So if you had to, and then if you change the force on it, you would actually change how you applied one force, you could actually measure a difference. So the fact of the matter is that there was no a priori reason for them to be the same. But Einstein said, no, let's actually make them the same. And this provided the basis for all of general relativity, because this is the concept that we call the principle of equivalence. And the principle of equivalence says, now, even further, it goes and says that there's no difference between a freely falling frame of reference and one that's far from a gravitational field. So you just fall the same way. And more succinctly, the laws of physics are the same for any freely falling observer. So you take a frame and you let it fall. Notice that this is different than special relativity. You take any frame and let it fall. Any freely falling observer sees the same laws of physics. Now, let's take it this way. That's different than special relativity. Special relativity says any uniformly moving frame of reference cannot be distinguished from any other uniformly. The laws of physics are the same for any uniformly moving reference frame. So one frame has one thing, another frame has another thing. They're both moving uniformly with respect to each other, not accelerating, not decelerating, not rotating. That's why I said that in the last lecture. So in that sense, they're different. So a freely falling accelerates. You can have something freely fall and accelerate. Well, how do we mean? Well, look at any image from the International Space Station. What are they doing? They're orbiting the Earth. They're falling. They're falling towards the Earth, but their lateral motion gets them so that they don't hit the ground. So as the International Space Station falls towards the ground, it's moving to the left fast enough that the Earth has curved away out from underneath it. And this was actually part of Newtonian dynamics, is that Newtonian dynamics said, hey, if you shoot something fast enough, the time it takes to fall, if the Earth's curvature is going out from under it, then the Earth, it'll rotate, it'll go all the way around. And this idea has been part of Newtonian mechanics for a very long time. In fact, Newton himself predicted this. It's called an orbit. And so another way to think about it is like, wait. Remember that the bullet or the cannonball that's fired from the top of the mountain that's going to go all the way around the Earth, it is falling towards the ground. It just has a lateral velocity that goes so fast that by the time it falls to the ground below it, the Earth's curvature has gone away out from underneath it. So When we say that the laws of physics are the same for any freely falling observer, that also applies to somebody in orbit. So if we look at people on board the International Space Station, they're floating, they seem to move, they appear to be weightless. How is that different than if we took the International Space Station and put it way out into deep space, just halfway to the next star, so that there is no gravitational influence? What would they do? They would float. Why would they float? Well, there's nothing to hold them to the ground, no artificial gravity. This ain't Star Trek or Star Wars where people walk around inside of a spaceship. There's no gravity in space. Well, there is gravity in space, but not far from stars. There's no thing pulling you down. So every space science fiction show that has spaceships, they always justify it by saying gravity plating or something like that, because otherwise, you got to always float your actors around. So in reality, if you were to take a spaceship and send it out halfway to the next star, everyone would float around. There would be nothing holding them, quote, down. There would be no such thing as down or up. You could design the spacecraft so that everything is on every side. And in fact, that's what they did with the Apollo spacecraft, is that switches and buttons were everywhere because, well, they would be floating. So if you go to the moon, you feel weightless, even though you're always falling. So there's no difference between weightlessness, meaning the feeling of weightlessness, and freely falling towards something, which is a statement of general relativity, the principle of equivalence. All right, since there's no difference, you couldn't tell the difference between whether or not you're inside a moving spaceship or not. So I'm standing here inside of this room, and I feel my weight on the ground. Good. Now, imagine, just for a second, that somebody comes along, maybe the Master from Doctor Who has incredible powers, and all of a sudden, they attach a whole bunch of rockets around the building that I'm standing in. And they attach all these rockets to the side of the building and magically remove the Earth from underneath me and turn on the rockets exactly at the same time, so the thrust is directed upwards. I couldn't tell the difference. Maybe there's a jolt. Let's assume that they're incredibly powerful and there's no jolt. There'd be no way for me to tell the difference between my being pushed down to the floor as a result of a gravitational pull or being pushed down to the floor because there's a rocket pushing me upwards. So if I took this room, attached rocket engines to it, sent it out into deep space, and put rockets towards it and accelerated it out to the left, I would feel a gravitational force to the left-hand side of the room, or one side of the room. Why? Because that's the direction, the rockets are accelerating me this way. So I'd feel a gravitational push that way. And I couldn't tell the difference between a gravitational push and an acceleration. So that's an essence of it. There is no difference between an acceleration due to gravity and an acceleration due to any force. And there's no way to tell the difference whether you're falling in a gravitational field or you're completely out in empty space and you just simply have nothing around you. Notice freely falling. There's nothing holding you up. You're falling in a uniform gravitational field. There's no difference between them. That's the equivalence principle. And so what this means is that special relativity can then be extended. And utilizing this idea, special relativity, which only discusses space and time, not really mass, it does describe energy, it describes mass in its own way, but it only says if you're uniformly moving, of a uniformly moving reference frame. It does not add the effect of mass on the surrounding space-time. And so when we think, well, wait a second, why do you fall towards the Earth when you're way up in space? Why do you fall? Because mass causes this gravitational acceleration. And so now we can start to bend the idea and say, well, wait a second. General relativity then says we add the effect of mass on space-time. Special relativity says there's no effect of mass on space-time. So what happens if we add the effect of mass on space-time? And that's what we'll get to next time. See you soon.